The second part of this section, section 2.3, involves higher order derivatives. As of now, we've been taking derivatives of functions, whether they're sums, differences, constants, whether they have constant multiples, products now, and quotients and trig functions. So we really have a pretty good toolkit of functions where we can take the derivative. But we're only taking the derivative once. We refer to this derivative that we've been working on as the first derivative. It's the first time you've taken the derivative of a function. Turns out that we can take the derivative of that function as well. And then we can do it again and again. These are called higher order derivatives. We have the first derivative, the second, the third, the fourth, the fifth, and so on and so forth. These are called higher order derivatives of our function. So let's take a look here at a function. This certainly is not a derivative. This is your function. But then we go ahead and we take the derivative, right? Y prime. We also call it f prime. We also use d dx as a verb to take action on our function, f of x. Oh, we also have dy dx too. There's just a number of ways that you can represent the derivative. There's actually 1, 2, 3, 4 different, there's even a fifth that we don't use that often, so I'm not going to mention that one. What's the second derivative? Well, that means you take this function and you take a derivative of it. So in a sense, you're taking y prime and you're priming that. Well, that's two primes, so that's y double prime or f double prime. Now think about what this verb does here. If there's two of them, there's two d's, like d squared, and there's two of these as well, although we don't put those in parentheses of the original function. And so that this matches that, basically d squared y dx squared is the second derivative. So we call this one the second derivative. This is the second derivative, and of course this one here is the first derivative. All right, so we can take even another one, successive derivatives. This would be y triple prime, which is f triple prime. That's 3 of these and 3 of these. So we've done that 3 times now, so they all piled up. Of the original function, of course, or d cubed y dx cubed. So what happens when we get to the fourth and fifth and sixth derivatives? Do we keep putting these hash marks here, these primes? We stop doing that around the fourth derivative. This is the third derivative. So this is the fourth derivative. And rather than doing 4 prime marks or hash marks, at that point, we put a number in here. This is the fourth derivative. And it's in parentheses so that we know it's not an exponent. This is the fourth derivative of x. You can still use the numbers here, though. Fourth derivative of that original function. Fourth derivative of that original y function. So this would be the fourth derivative. So we can really take as many derivatives as you'd like. So ultimately, we're down here at the nth derivative. We call this the nth derivative. And we can see there are 4 ways of writing it. Now, should taking the derivative of a function make the function easier or more difficult, more complicated, or less complicated? I think maybe a few examples will reveal that to us. Let's take a few successive derivatives. Let's get to those second and third and fourth derivatives. So if I had a function y equals f of x, and that function was 2x cubed minus 3x squared plus 2x minus 7. How's that? What's y prime, or the first derivative? Well, you can do this term by term, right? So the 3 will come down and hit that 2 with multiplication, 6. Deduct 1 from the exponent. This 2 will come down and hit that 3, that's 6. Deduct 1 from the exponent. This 2 is a constant multiple, and the derivative of x is 1. And then the derivative of a lone constant is 0. So f prime is 6x squared minus 6x plus 2. So f prime actually is an easier function. It's 1 degree less than the one above, and I'm not surprised because derivatives deduct 1 from the exponent. Let's keep going. Second derivative. That means do it again. So the 2 would come down and hit the 6 with multiplication. That's 12x to the 1 power deduct 1. Minus 6 is a constant multiple. The derivative of x by itself is 1, and the derivative of a constant all by itself is 0. So the second derivative is 12x minus 6. So we went from a cubic function to a quadratic right down to a linear function. Let's keep going with this and see where it leads. Third derivative. That's f triple prime, or third derivative. 12 is a constant multiple. It's along for the ride. The derivative of x is 1. And minus 6 is a constant. Derivative of just a constant is 0. So f triple prime is 12. Yeah, it does. It keeps getting easier and easier. These functions are getting simpler. That's just y equals 12. That's a flat line. One more, the fourth derivative. And now I can't really use the hatch marks anymore. I'm going to use numbers at this point. You put it in parentheses so you know it's not an exponent. It's actually a derivative. Well, wait a second. The derivative of a constant all by itself is 0. Fifth derivative. The derivative of a constant all by itself is 0. Apparently, once you hit 0, you're done. That's the end of it. And all the rest of our derivatives are now equal to 0. So it is true. When you take subsequent derivatives, each one gets easier and easier until ultimately you might hit 0. And if you hit 0, the rest of all the higher order derivatives must also be 0. So I guess we could say this. The nth derivative of the original function is 0 for all n greater than or equal to 4. Once we've hit that 4, this function is now 0. At least the higher order derivative is 0. Let's try some more. How about this function? F of x is sine of x. My first derivative, f prime. We remember the derivative of sine is cosine. Second derivative. Well, let's see. Derivative of cosine is actually minus the sine. Third derivative. The minus is a minus 1 multiplier. It's along for the ride. And the derivative of the sine itself is cosine. Let's keep going. Fourth derivative. The minus is just a constant multiplier along for the ride, and the derivative of cosine is minus the sine. What is my fourth derivative? Sine. Right back to the top. I don't think we have to keep going on this because it's all going to be repetition after that. I mean, I'll do a couple anyway. The fifth derivative. The derivative of sine is cosine. I think we saw that coming. So I think you can see the repetition here. I can see the repetition here. So there's a grouping here of 4 derivatives that just seem to repeat over and over and over. And that happens as well. In this particular example, we never did reach zero, and so we never actually were able to extinguish our derivatives. This thing's just going to keep going on and on. So all of our derivatives have some value, but we have to go hunting down what that value actually is, sine or cosine, or minus sine or minus cosine. Okay. So what I'd like to do next is I'd like to show you why we really use these higher order derivatives, and I want to show you what they mean. We do math not for math's sake. We do it because it describes how the real world works. We do it because we need math as the language of physics, for example, and of course we need math to do engineering, to make things. But primarily, we want to understand how the world works. So, if I were to show you the position function of an object. Let's draw a building here. And let's toss an object off the top of this building. Now, I'm not going to just drop the object and allow gravity to accelerate it. I'm going to throw it up into the air. It's going to reach some kind of pinnacle, and then it's going to come down here, and it's going to slam into the ground. It's going to be a parabolic shape like that. And let's say that the building is 100 feet high. And let's say the initial velocity that I throw the object up, and I'll say initial velocity equals plus because I'm throwing it up. That's the positive direction. And let's go up at, how about 10 feet per second? Okay? Now think about how that works. You throw something up with a certain velocity, it's going to go up for a little while, and then gravity is going to overcome that upward velocity. And then finally it's going to accelerate it as it comes down. Now the truth of the matter is, without wind resistance, an object would just continually be accelerated by gravity. I mean, just go faster, faster, faster. We know that's not really true because of wind resistance. Like a skydiver, for example, without wind, if there were no air, a skydiver would just keep going faster, faster, faster after they jumped out of the airplane. But we know that skydiver reaches what's called terminal velocity. So gravity's trying to make them go faster, and the wind is pushing back on them and preventing them from going any faster. Terminal velocity for a skydiver is about 125 miles per hour, by the way. So we're going to ignore the wind resistance, and I'm going to give you the position function. In fact, the only position I'm going to give you is y, which is the height. And here's the position function for this particular problem. It's going to be minus 16 t squared plus 10t plus 100. Now, I don't want you to just accept that on faith. By the end of this problem, you'll realize that that exactly describes the height of this particular object. Now, a couple things are going to happen here. One thing that's going to happen is this object will reach some kind of pinnacle right there. Love to know what that height is. I know that it's greater than 100 feet. The other thing is that the object will ultimately hit the ground right about here, and I know what the position will be, but I wonder how fast it's going. Just remember, gravity is going to accelerate that object faster and faster and faster with no wind resistance. So it's going to pick up quite a bit of speed by the time it hits the ground. Well, I've got some news for you, and that is that our calculus is what's going to be able to solve this problem. My question is how high and how fast? Those are my two big questions. Now, it turns out that the position function here is the location of our object. Now, I got to tell you that you notice the independent variable is time because that is the operative quantity in this problem independently. The time is marching forward. The object is going higher. The object's not going higher because it's going in an x direction. It's going higher because we allow time to proceed. So if you're going to take a derivative, you're going to take the derivative of the y with respect to the independent variable time. So it's dy dt. How does the height change with respect to time? Well, let's take the derivative. Minus 32t, because you deduct 1. The 10 is a constant multiple. It's along for the ride. The derivative of t is 1. Derivative of 100 is 0. So I have my first derivative. But think about what I just said about it. dy dt. Y is the dependent variable, but this problem t is the independent variable. That's time. I'm saying, how does time change with respect, how does position change with respect to how time changes? Position changing with time changing sounds like speed to me. So how does position change with respect to time? That's the speed. In fact, it's the instantaneous speed. In other words, you tell me what time it is, and I'll tell you how fast this object is moving in the y direction. So this is the interpretation of the first derivative. First derivative, that's speed. In fact, since it's speed, I guess we could even give it a name, velocity, the v of t, the velocity function. You want to know the object's velocity? Use this function right here. Okay, so how can we use this to figure out how fast it is when it hits the ground? First of all, let's figure out how fast the object is traveling at the very, very, very beginning of the problem. Now, the beginning of the problem time is 0. So what's the v of 0? Make sure this works. Yeah, that is correct, 10 feet per second. And based on symmetry, I would imagine that at this moment right here, that your object is traveling at minus 10 feet per second, because minus means down. So by the time you get here, how fast is it going? Minus 20, 30, minus 100? I'm not sure. I guess the most important thing to do right now is figure out, well, what time is it when it hits the ground? You don't need calculus for that. So set y to 0. Let's find out what time it is. How long does it take to get down there? Y equals 0, y equals 0. Well, I think we could probably factor this problem a little bit. Let's take out a common factor of negative 2, and let's see where that leads us. Negative 2 comes out, and I have 8t squared minus 5t, and this will be plus, minus 50. Now, I don't see any other common factors in here, so I would divide by negative 2, make it go away, and I would get my quadratic equation. So when is y equal to 0? At 2 different times, because that's what t squared is telling me. There's 2 different answers. I'm afraid this is not factorable. So because it's not factorable, I'm going to have to use the quadratic formula to get this. So the quadratic formula says it's negative b plus or minus the square root of b squared minus 4ac all over 2a, where this is a, b, and c. That's 5 plus or minus b squared. That's going to be negative 5 squared is 25 minus 4 times a times, careful, c is negative, all over 2 times a, which is 2 times 8. So the magic times are 5 plus or minus the square root of, let me work all that out for you here. Luckily, that's a double negative, by the way, so that actually adds together. So I'm getting 25 plus 4 times 8 times 50. So I'm getting a big number, 1625 in here, all over 16. Notice it says plus or minus. There are 2 answers. Let's do both. The square root of 1625 plus a 5. Divide that by 16. So here's 1 time. And now let's do 5 and subtract the square root of 1625. Let me see what I get in that case. And then, of course, let's divide the whole thing by 16. Here's the other time. All right. This is a real-world problem, so I don't think negative time makes any sense. This problem starts at 0 seconds, so whatever happens before then is irrelevant to this problem, so let's throw that one away. Okay, we know when it hits the ground at 2.83 seconds. Let's go back and label that this happens about 3 seconds into the problem, so I wonder how fast it's going. Just plug it in. So I'm going to plug in my speed, into my velocity function. We have a velocity function that says minus 32t plus 10. We already know v of 0 is 10. So what's the v at 2.83 seconds when it hits the ground? That would be minus 32 times 2.83 seconds plus 10. Remember, this better be a negative velocity because it's going down. So 10 minus 32 times 2.83 is negative 80.56 feet per second. That's pretty fast. All right, what's the first derivative? It's a rate of change. And in this case, it's the rate of change of position versus time. That's just speed. So this first derivative can calculate speed wherever you like. It can calculate, now by the way, this is only the vertical speed. The up and down speed is not the horizontal speeds. But I know the vertical speed coming down is negative 80 feet per second. So the next question would be this. When and how high does this object go? So when does this happen? When does it reach the pinnacle? And how high is it when it reaches the pinnacle? So I want you to imagine if I threw this pen up in the air, straight up in the air, it would go like this. It would go up here, and then it would stop for just a moment, and then it would come down. In order to change from positive speed to negative speed, you have to go through speed 0. So it goes up, stops, and then comes down. What is the vertical speed at this moment? It's 0, actually. And so that's how we'll discover what time it is when that happens. So let's take the velocity function and set it equal to 0. When is the speed 0? What time is it? So negative 32t plus 10 equals 0. Subtract 10. Negative 32t is equal to negative 10. Divide by negative 32. Divide by negative 32. Boy, it didn't take too long, I guess. So 10, 32. It only takes 0.3125 seconds for that to happen. That's the when, okay? Speed is 0 at about a third of a second. Now the where. Now if you look at the picture one more time, you'll notice that we threw this object up from 100 feet. So this should be 100 and something feet, right? It should be a little higher. And where are we going to get height information? Right here. So it should be a little higher than 100 feet. We didn't give it much time to get there, but this function should give that result to me. So let's go ahead and get our position. So y equals negative 16 any time squared that you're at, plus 10 times time plus 100, but we're currently at 3.3125 seconds. Now make sure it makes sense. It should be a little bit higher than 100, right? Let's calculate this. 100 plus 10 times 0.3125 minus 16 times 0.3125 squared. I've got it into my calculator here. Better be bigger than 100. It isn't much higher, is it? 101.5625. Apparently, we didn't throw it upward with very much initial velocity. I should have given it some more initial velocity, so I just kind of threw it up about that much. So I only got an extra foot out of it. But we knew when it happened. It took a third of a second, and we knew exactly how high it was when it started to plummet. And by the way, it accelerated to be pretty fast, about 80 feet per second down. Now, the last thing I'm going to leave you with is this. Little summary. The summary of this problem is that we have a position function, y. We have the derivative, the first derivative of y, which we also refer to as the velocity function. And here come your higher order derivatives. Guys, let's do this one more time. So y prime, y double prime means one more derivative, please, through d dt of your velocity function. Now, the minus 32 is a constant multiple. Derivative of t is 1. Derivative of a constant is 0. So it's minus 32. And what this reads to me as, how does velocity change with respect to time? So rather than just being a math problem, I'm interpreting what derivatives truly are. They are rates of change. They're all speeds, but the first one was the speed based on a position changing with respect to time. This one is a velocity changing with respect to time. When you get in your car and you want your velocity to change with respect to time, what do you hit? The accelerator. How do you change velocity? You have to accelerate or decelerate, which would be a negative acceleration. This must be acceleration. And that's exactly what it is. In fact, now I'm proving to you that we got this problem right, because we're here on Earth, and this truly is the acceleration on Earth. The acceleration on Earth is minus 32 feet per second squared. It's accelerating downward. And if this were in the metric system, it would be minus 9.8 meters per second squared. So that is the right acceleration. We're on the right planet here. So higher order derivatives, and now you know that derivatives are rates of change. It's how something changes with respect to whatever's on the bottom changing. And that could be time in this case.